setting up. Need about 30 seconds to set up. Okay, great. Now we are on both sides on Zoom and the YouTube side. Let me start with a very brief introduction for our speaker today. So today is our ending talk for 2022. So we are very happy to have Dr. Pen Chen to introduce his research work using the LBM method. Chen Peng obtained his PhD from the Department of Mechanical Engineering at the University of Delaware. So after his PhD, he worked as a postdoc in the Department of Energy and Mineral Engineering at Penn State University. So in 2020, he joined the School of Mechanical Engineering at Shandong University, China, as a faculty member. So Dr. Peng's research mainly focus on developing numerical method for multi-phase flow and studying the flow physics in turbulent and particle-laden flows. So he received the ICMMES CSR Award from the International Conference for Mesoscopic Method in Engineering and Science in 2019. He also published a lot of journal papers in using LBM methods for turbulence flow. So then I leave the to Dr. Peng.
Thanks for the introduction. It's a great pleasure to share my research with all of the audience. I would like to apologize to my audience first. I'm still in the recovery process. So I usually cough badly. So like if I cough, I drink water or like take some mint to help me get through this talk. I would like for you to forgive me. So my talk today is about the application of the Laden-Boltzmann method in the study of turbulent flow laden with finite-size particles. This actually is a topic I started to do during my PhD, and currently, like I think right now the code is pretty mature, so like I mainly use this method to study the flow physics. So this is a brief outline of the content in this topic talk. First, I will give a brief introduction about what is a particle-laden turbulent flow and what is the particle-resolved direct numerical simulations. And also, I will give a brief introduction of the Laden-Boltzmann method. Because from my understanding, this is a serious seminar, so like you might have already heard from other speakers about this Laden-Boltzmann method. And my focus about this method is mainly on its boundary treatment. Currently, there are many, especially this boundary treatment on a no-slip boundary. Specifically for my case is the no-slip condition on the particle surface. So there are mainly two categories. The first is a bounce back schemes, and the other one is the immersed boundary method. Some of you may are familiar with the conventional safety method, may have heard about this one. It's a very usual one used in many fields, such as like fluid structure interactions. And also I will share some applications of the particle resolved direct numerical simulations. And finally, I will give a brief conclusion. So what is the particle-laden turbulent flow, or some in some literature is called dispersed turbulent flow. It's basically a turbulent flow. It's a multi-phase turbulent flow. A turbulent flow laden with a dispersed phase, which usually could be some solid particles or like a liquid droplet or bubbles or small bubbles. In my case, it's mainly particles, which means the interface is a fluid, a solid interface which cannot deform. It's basically rigid particles. So this dispersed turbulent flow, you can find it in many nature phenomenon and this engineering applications, such as this sandstone, this famous picture of a sandstone in Arizona. And this is the rain formulation, rain droplet falling. This is also a particle laden flow. If the rain droplet is very small, of course, at this stage, in this picture, you can no longer consider these droplets as rigid particles, because its size is big enough. Its surface tension cannot hold it a spherical size, so it will have some deformation. But when the droplet is still very small, you can still consider it as a rigid particle with a spherical shape. And also, this dispersed turbulent flow can be found in many engineering applications, such as this fluidized bed, and we studied the dispersed turbulent flow, especially how the particle interact with the flow to help us to form a better understanding of these natural phenomena, how to prevent them, how to predict them, and for this engineering applications, how to optimize this. So there are two. So what do we study in this turbulent dispersed flow? So there are two essential questions to answer. The first is, how does turbulence affect the particle motion? For example, like in this mixer, we basically stir this flow field, and we hope it to the turbulence to distribute the particles as uniform as possible. But this is not always the case. I mean, even for some particles, for example, when the particle inertia is relatively small or comparable to the smallest eddies in the turbulent field, even in the homogeneous isentropic turbulence, the particle will not distribute uniformly. So we want to change. In this case, like if we understand how the particles, how the turbulence affect the particle motion, we can modify the turbulence to make the particle distribute more uniformly to help the mixer work more efficiently. This is one application. Of course, we also care about how turbulence will affect the drag of a particle in the flow field. So basically, how would the drag force on the particle change when it's in the turbulent field compared to it's in the laminar flow? For example, this application is like when you have some particulate matter. We want to understand how its sedimentation efficiency is, like how it will be affected by turbulence. And also in the cloud physics, like we also care about how does turbulence affect the collision rate of the particles. Like the more this small droplet collide, the quicker they will form the rain droplet, and once it's reached a certain size, it will falling down, and you will see the rain. So this is the first question we want to study. The second one is like how do particles modify turbulent flow? So it's basically an interaction between the dispersed particles and the carrier turbulence. So not only the turbulence will affect the particle will also affect the turbulence. This also have a lot of applications. For example, the flow drag, how the particles affect the flow drag of this pipe flow. Say you see a firefighter here. So if you this is actually a quite a famous phenomenon. Is that once you add some like say high this long chain polymer into this flow, you will greatly reduce the drag in this pipe, drag coefficient in this pipeline, and under the same pressure, this water jet can go for much longer distance, and this had a very important application to save lives. And another thing is that how do particles affect the turbulent intensity? So basically, we have a turbulent field. Can we use the usually like people will think turbulence is something you cannot control. But there's one thing you can do is that you can think about is that can we like add particles into this turbulent field to control its intensity? Like if we don't want this much turbulence, can we add particles so the turbulence will reduce as a laminar? It's more like a laminar flow, or like in the inverse case, for example, in this mixing tank case, we want more turbulence. So can we add particles to do that? So the difficulty of answering these two questions is these are not usually coupled. So if you have a dispersed particle phase and a carrier turbulence phase, these two will happen simultaneously. So you cannot separately do that. You cannot answer them separately, and this coupling will greatly make the problem more complicated. So how do we study this turbulent dispersed flow? As all the other fluid mechanics problems, we can do experiments and we can do numerical simulations. And because it's turbulent, so the theoretical analysis only has limited use because it's a very nonlinear system and it's a multi-phase system, so it's quite complicated. It's very difficult to do theoretical analysis. So usually you can only do experiments or like numerical simulations. And of course, both methods have their own advantages and disadvantages. The main advantage of the experiments is that it's physically reliable. You get what you see, and it's because it's a realistic physical condition, which means like you can have a very complicated boundary shape. In the numerical simulation, on the other hand, is kind of difficult to realize. The numerical simulation at this moment are still constrained to some ideal conditions, such as this homogeneous turbulence or this channel or pipe simple wall-bounded turbulence. And of course, the disadvantage of experiments is still relatively expensive to conduct. Another thing people may not realize is that because we want to study the physics of how the particles interact with the flow, we have to make a very accurate measurement of the flow field around the particle. And this is not easy. Even right now, the best PIV at this moment can like the resolution can be like sub micron, but it's still difficult to have a very accurate measurement. If you look at the papers about experiments, it's usually quite noisy. And of course, another thing about these experiments is that you can measure the flow field in a limited region. It's very difficult for you to give the information of the whole flow field, but this can be done easily in the numerical simulation. But of course, for numerical simulations, as we said, it's basically its advantage is the disadvantage of the experiments. It's relatively inexpensive and also it can easy access to the local flow data, but it's limited to very idealized physical conditions, and it's only reliable when properly conducted. So if you don't do it carefully, then basically what you get is trash. So how do we choose? How do we? So my research is more about using the numerical methods to study the turbulent dispersed flow. So how do we choose the numerical methods? The choice of the simulation method, of course, should depend on the specific problem. And in this turbulent dispersed flow, usually we have three criterion. The first one is the particle volume fraction. So the particle volume fraction. So if the volume fraction, is very small, then you might ignore the effect of the dispersed particles on the turbulence. So because it's volume fraction, you can think it's like you have a large pot of soup, and you just add a little salt in it, and it will taste like nothing. So the same thing. If you have a very low particle volume fraction, you can ignore the effect of the particle on the flow. But if you have a very high or like not so low particle volume fraction, then you have to consider about the interaction between the particle and the fluid. And if you further increase the particle volume fraction, then the particle will have some interaction. The particle will collide with each other, even form the clusters, particle clusters. And also the other two the other two criterion are the particle Stokes number. Basically, particle Stokes number is a measurement for the particle inertia. What does that mean is basically means if the particle has a very small inertia, it will quickly respond to the flow. So basically, you have the same velocity as the ambient flow. So there is no necessary for you to like track the particle motion. You just solve the concentration, extra concentration equation for the particle concentration. That's fine. If the particle inertia is not so small, then if it's still small, then you can write the particle velocity at expansion, asymptotic expansion of the flow velocity. And at this case, you still don't have to solve the individual particle motion. But when particle has a very large inertia, meaning it starts not to follow the particle, the fluid motion, then in this case, you have to use what we call Lagrangian particle tracking. Is that you have to track the individual particle motion. And the last criterion is the particle size. So if the particle is very small, it's much smaller compared to the smallest eddy, the size of the smallest eddy, which is a cosmograph length in the turbulent field, then you can think the presence of the particle will have no effect on the flow structure. However, if the particle has the particle size is comparable, even larger than the cosmograph length, in this case, we call it a finite-size particle, which then the particle will create the discontinuity and the distortion to the flow field. Then in this case, you have to rigorously resolve the no-slip condition on the particle surface if you really want to accurately describe the particle fluid interaction. So for the fully resolved methods, the bottleneck is to represent the particle fluid interface accurately with the accepted cost. Basically, this, in short, this means how can you efficiently treat the no-slip boundary condition on the particle surface. And there are two categories of methods. The first one is called body fit methods. This is basically remesh. Once your particle move, you remesh the computational mesh grid, and you always solve the Navier-Stokes equations in a time-dependent domain subject to the change of particle interface. The advantage of this type of body fit methods is that it's very accurate. And because you always have the grid node on the particle surface, it's very easy to certify the no-slip condition. Of course, the disadvantage is that it's required frequently remeshing. It's very expensive, especially when you have a lot of particles, and especially you're dealing with like three-dimensional simulations. And examples of these body fitted methods include these arbitrary Lagrangian Euler methods and overset meshes, and all of them have been used in the particle-laden turbulent flow simulations, but limited to a very small number of particles. The other type of method is called Eulerian method. Basically means you solve the flow using a fixed Eulerian grid. The grid mesh will not change during the simulation. However, because you have a moving particle and you have a particle with this curved surface, curved shape, so the grid line will not align with this, will not always align with the particle surface, right? You won't expect the grid node to collapse with the particle surface location. So then you have to figure out efficient techniques to treat the no-slip boundary condition on the particle surface. And of course, during the years, there are many boundary treatment techniques have been developed. For example, the most famous one is the immersed boundary method. This has been used in many applications, not just the particle-laden turbulent flows. Of course, for particle-laden turbulent flows, what we said immersed boundary here is the diffuse interface immersed boundary. It's not the sharp interface immersed boundary, because the diffuse interface immersed boundary method has a smaller so-called grid locking, meaning the Gaussian invariance is better preserved when you have a diffuse interface. So what we call immersed boundary here is specifically for the diffuse interface immersed boundary. And also this directed forcing fictitious domain method, this has also been used by many people. And for Zales, this is a very special method which basically assumed there is a So it basically assumes that the flow very close to the particle surface always satisfy the Stokes flow condition, because of the no-slip condition, the flow around the particle surface had a very small velocity difference with the particle surface. So you can use the Stokes solution to expand the flow velocity in that phase. Then you have only to map in the flow of the near the particle surface and the far field. And this method is quite complicated. We have some experiments. We have some experience of this, but this is not easy to use compared to the other methods. The last one is the lattice-Boltzmann method. Of course, it is actually inappropriate to put the lattice-Boltzmann method here, because lattice-Boltzmann method is not a boundary treatment technique. It's more, lattice-Boltzmann method should be classified as like a flow solver. It's like a finite difference or finite volume or finite element. Or spectrum method is not a boundary treatment technique, but the lattice-Boltzmann method has its own this very unique no-slip boundary treatment technique called bounce back schemes, which is very efficient way to treat the no-slip boundary conditions. Of course, as we want to emphasize here, there is no universal suitable approach. The choice of the method depends on the problem. If you have a very small number of particle, and the particle motion is easy to describe, for example, if you have a fixed particle, then it's not wrong to use these body fit methods. Okay. Excuse me. The O'Leary method, of course, are more suitable for flows with large number of free moving particles. Okay, so let me briefly introduce the lattice-Boltzmann method. So what is a lattice-Boltzmann method? In short, the lattice-Boltzmann method is an indirect way of solving the incompressible Navier-Stokes equations. So the governing equation of the lattice-Boltzmann method look very different from the Navier-Stokes. So this is Navier-Stokes here. Of course, for the incompressible Navier-Stokes, it's just a velocity divergence is 0. This one can also be simplified, but that's not essential here. So the governing equation of the lattice-Boltzmann method is very different. So like some people may think, well, it's a magic. Like it's magic. How can you solve this equation? So to solve the flow field, which is governed by these physical equations. Well, I would say, in short, you only need to. So if you have this physical Navier-Stokes equation, of course, the most straight way, the first way in your mind how to solve it, you might think, okay, I would directly discretize it in both space and time, right? Then I just take forward in time, solve it, discretize. This direct discretizing leads to finite difference, finite volume, or finite element, right? And another way to do is that you can use some kind of transform. Okay, let's call just lattice-Boltzmann transform. We can use the lattice-Boltzmann transform to project this equation into another space, and we solve this equation in another space, and then we project it back to get the hydrodynamic variables we want. And this is not strange, because there's a famous method called spectral method, does the same thing. So what is spectral method is to take the Fourier transform of this Navier-Stokes equation. Then you solve this Navier-Stokes in the Fourier space. Then you project it back. You do the inverse transfer, inverse Fourier transfer. Then you get the velocity pressure in the physical space. So Lance-Boltzmann method has nothing, I mean, in theory, it has nothing different with the Fourier space. It's just because the Lance-Boltzmann space is not familiar to people. It's not the Lance-Boltzmann transformation is not so familiar to people as the Fourier transform. But after Fourier transform, the equation will also look different from this Navier-Stokes. But this Lance-Boltzmann transform is just a little bit more strange. So the Gaussian equation looks slightly even more like this guy. But this is not magic, and you can prove the projection mathematically by a lot of methods. The most typical one is the Chapman-Enskog analysis. This is a multi-scale expansion method. So what is the disadvantage and advantages of the Lance-Boltzmann method compared to the conventional Navier-Stokes solvers such as finite difference, finite volume? First, if you look at this equation, this Lance-Boltzmann equation, you can see this is except for this term. This term is on t plus delta t. All the other terms are on on the current step, which means it's an explicit equation. It's very easy to code. You just move this guy to the right hand side, then you solve, because all the information here are known. So it's very easy for you to code, and it's also more flexible in the boundary treatment. It's can not only use the boundary treatment techniques of the conventional CFD methods, it also has its own unique boundary treatment techniques. It also avoid solving the pressure Poisson equation, because in the LBM you can get the pressure by directly taking the moments of this f, which is the distribution function. And but for finite difference, finite volume, for the incompressible Navier-Stokes, you have to solve the Poisson equation to get the pressure, and the Poisson equation needs some iteration and the global communication, which is computationally expensive. But of course, at this moment, generally speaking, the Navier-Stokes solver is still less computationally expensive than the LBM, because of course the LBM equation is easier to solve, but you have more equations to solve. Okay, so the last advantage of the LBM is its intrinsic second order accuracy, and it's had very small numerical diffusivity. Of course, we say no pains, no gains. So there are also many disadvantages about the LBM, and we should not avoid this, right? We should not. The first one is higher in terms of computational cost. I said at this stage, I will still say LBM has no computationally advantage compared to the Navier-Stokes. Especially if you use CPU computing. If you use GPU, you might draw a different conclusion. But for the future, I mean, because LBM has a very good advantage is it have very good scalability. So basically, you have like 10,000 processors. You have like a million processors. It will not affect its computational efficiency. And this is very difficult for you to do for conventional Navier-Stokes solvers. So in the future, maybe the LBM in terms of computational efficiency can beat the Navier-Stokes solvers. And the second disadvantage of LBM is restricted to the isotropic homogeneous mesh. And it's basically meaning you can only have this cubic, in 3D you have this cubic mesh. This is not suitable for some very anisotropic and inhomogeneous flow. And I had some experience of developing some non-standard LBM, but those models are not so numerical stable. The third disadvantage is that although we said the advantage of LBM is it has intrinsic second order accuracy, the disadvantage is that it's very difficult for you to improve it to higher order accuracy. So you basically you're restricted to the second order accuracy. And of course, the last one is the last disadvantage is very worse. It has worse numerical stability because of its very small numerical diffusivity. Of course, people have developed some improvements to solve this problem. So LBM, as we said, it has so many disadvantages. So why are we still using it for to conduct fully resolved direct numerical simulations for particle-laden turbulent flows? This is because, yes, we said LBM has so many disadvantages, but once we discuss this specific problem of particle-laden turbulent flow, most of LBM's disadvantages are gone. So LBM, it is true, it has higher computational cost, but the bottleneck of doing this particle resolved or fully resolved direct numerical simulation is how to treat the no-strip boundary condition. So as long as you can do this no-strip boundary condition treatment very efficiently, you can actually compensate the higher computational cost. Okay, so the second one is it's restricted to the isotropic homogeneous mesh. So I would never recommend people to use the LBM to simulate, like say, single phase turbulent channel flow. Of course, you can use it as a validation test, but you shouldn't use LBM to study this. The final difference or final volume does much better because LBM for this flow is much more reasonable for you to use this very non-uniform and non-isotropic mesh. But for the particle-laden turbulent flow, no matter what method you choose, you use finite difference, you use LBM. Almost all the studies they use this uniform mesh because this is halfly because when particles moving around, say you have for single phase flow, of course you can have a very dense mesh near the wall, and you have a very large mesh on the channel center. But if you have a particle, the particle move from the channel, to the channel center, then you have to like say increase the grid resolution in this region. So the most efficient way in this case is that let's just use the uniform mesh. So the restrictor to the mesh restriction in the LBM is no longer a problem, and it's difficult to improve to the higher order accuracy. The one thing I want to point out is that popular schemes of the boundary treatment, such as the immersed boundary method, is even only first order accurate. And we know that the Navier-Stokes equation is an elliptical equation. So if the boundary treatment is only first order accurate, then there's no meaning for you to increase the accuracy of the flow solver. So this advantage of difficulty to improve to higher order accuracy is also no longer disadvantage. The only one remaining one is the numerical stability. And this is the only remaining issue. But there are ways to overcome it. But to be fair, I would, from my own experience, I would still say LBM, in terms of numerical stability, LBM is still worse than the conventional CFD methods. So the computational, this is just some comparison between our LBM code with our collaborators from Europe, and also our own test on the stability of the LBM. So for single phase simulation, if you have smartly design the algorithm of how you conducted the kernel algorithm of the LBM, then you can have almost ideal stability, speed up for particle Laden flow. If you use careful design how you change the data, then this will not affect the speed up that much. It's still close to ideal. So we also compared our LBM method with the different final volume immersed boundary. For single phase, we are about the same, I would say, as same order. But for particle Laden, our code still needs some improvements. But this does not mean the LBM method is much worse than the final volume immersed boundary method. It's just like our code is not as much optimized as the other people's code. So how do we treat it? As we said, the efficiently treating the no-slip boundary condition on the particle surface is a key. So how do we treat the no-slip condition? There are two ways. The first one is to use the so-called interval bounce back. The idea is to directly construct the unknown distribution functions based on the known ones and the hydrodynamic constraints. For example, if you want to, the kernel steps of LBM is that you do the collision, so-called collision on this each node point, then you exchange the distribution functions between neighboring nodes. So in LBM, if you in the solid region, there is no distribution function. For example, if this is wall, this is solid region. On the right hand side of this wall is the solid region. Left hand side of this wall is a fluid region. Then there is no distribution function here. So how do you? But you still need to get the distribution function for this fluid node point. So how do you get that? You have to construct it. So the interval bounce back is a way to construct, and interpolation is so if it's just a bounce back, meaning like this guy goes to the wall, just a bounce back and return to this when this wall is not half grid space from this node point, it only has first order accuracy. So interpolation basically meaning you use interpolation to better construct this guy to maintain the second order accuracy. Of course, you can do a spatial interpolation, meaning you use multiple points. But in particle Laden flow, if you have very dense particle suspension, then you may only have one free node point here. So then in this case, you can do tempo interpolation, meaning you only use the distribution function at this point, but you do it you use the information before the collision and after the collision to do the tempo interpolation. And the interaction, the force and torque acting on the solid phase is easy to compute. You just count the momentum gain and momentum loss during this bounce back process. And the advantage of this interval bounce back is it can ensure second order accuracy under all circumstances. And it may sound easy to you, but it's not easy at all. I mean, as we said, the mainstream method, such as immerse boundary method, only has first order accuracy. The potential problem, and there are some, for example, lack of instantaneous scattering invariance. Of course, this problem is not just a problem of LBM, it's a problem of all the O'Lary methods, which means the force, we know that the scattering invariance basically means the force and torque should not change when the reference changes, right? But this is not the case for numerical simulations. The force and torque acting on, say, a particle, an immersed particle, is actually depending on how this particle align with this grid mesh lines. Okay, so this lack of instantaneous scattering invariance is a general problem for all the O'Lary methods, but for LBM, it could be worse. As we said, it's LBM, the boundary treatment is more accurate. The accuracy and the robustness are not always consistent. I should say it's always conflict with each other. So the other potential problem is not strictly certified mass conservation. This is not a big issue for the applications such as particle Laden flow, but it may be a issue for the multi-phase simulations. It also requires for refilling. The refilling means like because we have no distribution functions in the solid region, but as we can see from this plot, once this node point, say this solid, this dash circle is the particle location at the t times step, and this at the one time step later, it's moved to this location, this solid dash, solid line. So then this node point switch from the solid node to the fluid node. So in this case, you need to initialize the distribution function at this node. And this one, if you do not do it properly, it will cause huge numerical stability issue for your simulation, as we see here. If you don't do it properly, some of the initialization process algorithms in the literature are not stable, are not suitable for the particle Laden turbulent flow because it's a numerical stability issue. So the immerse boundary method is the immerse boundary method for LBM has no difference from the immerse boundary for the conventional CFD. It's basically you evolve the flow field without without considering the force. So the idea of the immerse boundary method is to assume the whole flow field, whole flow domain, even the solid particle region are filled with fluid, and use the no-slip boundary, the no-slip constraint on the boundary is converted to a force acting on the ambient flow. So the immerse boundary method, you first evolve the flow field without this forcing, then you get the temporal velocity, and you use this velocity to do the to interpolate this velocity to the particle surface, to the Lagrangian point, Lagrangian tracer particle point, on the particle surface. Then you take the difference. This is the target velocity. This is the velocity satisfying the no-slip boundary condition, and this is the velocity, temporal velocity. And you take the difference and you get the force. Then you do the inverse interpolation to interpolate this force on the particle surface to the neighboring fluid nodes, and then you finally use this force on the fluid point on the node point to correct the velocity. The advantage of the immerse boundary method is, of course, it's because this by interpolation, which is actually provide you some numerical diffusivity, which increase the robustness of the moving boundary treatment. It has less force fluctuation, and because you already have the velocity, you have fluid everywhere. So when you use immerse boundary method to treat the no-slip boundary condition, you have the distribution function, already have the distribution function in the solid region. So there is no need for the refilling, basically meaning the initialization on the newly covered, uncovered fluid node. The disadvantage of the immerse boundary is only first order accuracy, do not satisfy rigorous no-slip condition. This one is this first order accuracy. I mean, if you are not so concerned about the very specific flow around the particle, then this may not be a big issue, because as long as you have enough grid point, first order accuracy may still give you pretty accurate results. Do not certify rigorous no-slip condition. This is also not a big issue. You can use there are some solutions to this problem. The real issue I see from my own experience about this immerse boundary method is it cannot compute the velocity gradient correctly near the solid surface. What do I mean by that? This problem is because the immerse boundary methods change the physical equation of change the physical momentum equation. So we take this simplest equation of this turbulent of this laminar channel flow, which you certainly know this guy has an analytic solution, right? So the physical condition is this guy, okay? So by taking one integration, then you get the velocity gradient. You take another gradient, you get the velocity, and this is an analytical solution. But for the immerse boundary method, it's no longer solving this equation. Within this diffuse interface, you are actually solving this equation. Okay, of course, I use the cosine delta here. You're no longer solving this physical equation. So if you solve this, if you integrate this equation, you'll realize that for the velocity gradient outside this diffuse interface, you still have exact solution, but within the immerse boundary, this interface, you will have a arrow on the order of 1. This basically meaning the gradient can be you can have like a arrow as large as 50%. Okay, and if you further integrate this velocity gradient to get the velocity, and then you can prove the immerse boundary is indeed first order accurate. Okay, you have a first order accurate here, and this problem cannot be solved as long as you modify the physical equation. You always have this. Okay, and this what the consequence of this? And you see, if we have a particle in the turbulent field, and if we plot the dissipation, the dissipation of turbulent kinetic energy as a function of the distance from the particle surface, you will see that the dissipation will increase monotonically as it approaches to the particle surface. However, this is not the case when you use immerse boundary method to solve that. You will have a drop of this dissipation rate near the particle surface because you cannot calculate the velocity gradient correctly. Okay, so the dissipation rate plays an essential role in the turbulent particle laden flow simulations. That's why, like I would say, the local results, like near the surface, is not so reliable, I would say. This is like this is why, like, despite there are so many papers talk about their particle resolved direct numerical simulation for particle laden turbulent flows, you seldom see this local profile, especially near the wall. Okay, this is a big problem of the immerse boundary, as we see. So of course, we have done some comparison between the immerse boundary method and the interior bounce back method schemes. For example, for this Taylor credit flow, this 2D flow has the analytic solution, and we can numerically also confirm that the interior bounce back not only ensures second order accuracy, but also its error is much smaller than the immerse boundary method. Okay, and of course, the immerse boundary method also has its advantage. When you compare the for this cylinder settling in this flow, if you measure the instantaneous force acting on this cylinder, you will see that when you use immerse boundary, you have less force fluctuation. Okay, this high frequency fluctuation is numerical error due to the lack of rigorous Gary invariance. Okay, and for the interior bounce back, it's worse. You have much larger this fluctuation. So we also directly compare this interior bounce back and the immerse boundary in a particle laden decaying homogeneous isotropic turbulence. And I mean, if you look at overall turbulent kinetic energy, because it decaying turbulence, the turbulent kinetic energy will decay with time. And if you look at overall results, the LBM and the immerse boundary, the IBB and the IBM, they have the very similar results. But if you look at the local profile, the interior bounce back is much more trustworthy. So that's why, like, we still prefer to use the interior bounce back as our boundary treatment. So I have the brief summary of the comparison between the interior bounce back and the immerse boundary. And I'm not gonna repeat this since I have already covered this in the previous pages. Last, I will I will show some quick results of some representative particle-laden case, particle-laden turbulent flow simulations with the Laden method. This is the particle-laden homogeneous isotropic turbulence. The main purpose of this is to study like how the turbulent kinetic energy and dissipation rate changes with these non-dimensional parameters, and we finally generate some models for the turbulent kinetic energy and dissipation rate. And this is a particle-laden homogeneous shear turbulence. This is something I have done very recently, and the shear turbulence. This homogeneous shear turbulence is not something generated by the two solid planes. It's actually the particles and fluid can get through this top and bottom boundary, and this is done by so-called shear periodic boundary, and the treatment of this shear periodic boundary needs some techniques, and finally, yeah, this is something we have recently done, and as you can see, the particles breaks the these large vortex structures and creates these small vortex structures. This is actually a very well-known effect of how particles affect the turbulent structures. And this is the particle in a free streaming turbulence. Basically, you generate turbulence here, then you add a mean velocity, so the turbulence will free streaming and passing a fixed sphere. And in this case, what we are interested in is how do we model how would this the drag force on the particle change compared to the laminar flow, and how would it depend on the parameters, the physical parameters, and we generate this model. This is a particle-laden turbulent channel flow, and the main purpose of doing this is to study how the particles change the turbulent kinetic energy budget in this flow. And one thing I want to point out is that this is actually a technique. How do you maintain the numerical stability when you have these particles? So when you have this, when you try to do this, when you add particles into this flow field, if you directly put particles in, then your code might diverge very quickly. The better way to do it is to add these particles as small seeds, then make it grow gradually to its final size. So this is a way this is a very good trick for you to maintain the numerical stability. We can do that because we only interested in how the flow statistics change when the flow reach the fully developed stage, the particle-laden turbulent pipe flow, and we want to see how the curved wall will change this modulation mechanisms. And this is something also I have done recently. This is like I expand previous case. The particle are spherical particles, which is easy to handle its shape and particle interaction. But how about the more complicated result, more complicated particles? For example, in this case, cylinder particles, and it has a very complicated this particle collision, and we made this code, and we try to study like how the drag in this channel changes with the aspect ratio of these cylinder particles. And finally, a brief summary of what I have discussed. Again, I want to emphasize that there is no universal good numerical methods for all fluid dynamic problems. I don't want to advertise the last boson method for all the fluid mechanics problems. I know some people may have done this, and once like people have heard about this over advertising, and they use the LBM for their own problems, and the experience is not so experience is not so good, then the people will they will fully abandon LBM. But this is something we will try to avoid. But the features of the LBM does make it very suitable for particle-laden turbulent flow studies. And with recent progress, LBM has been successfully developed as a reliable tool for fully resolved the DNS of particle-laden turbulent flows. And this has been actually quite recognized by the fluid mechanics community. And in at least 2 annual review papers, LBM has been included as a representative method for this type of problem. And of course, the LBM still needs a lot of improvements, especially the bond treatment still has some issue, and also how do you deal the particle collision lubrication force, how do you reduce the force fluctuation, and how do you maintain a better numerical stability for higher Reynolds numbers. That's something still needs to be done. Okay, that's all about my talk. Thank you for your attention. I might have exceeded a lot of time. Sorry about that.
Yes, thank you, Dr. Peng. Very interesting talk, and a very systematic introduction about how to use the LBM to do the particle-native and turbulent flow. So then we will enter the Q&A time. So if our audience have any question, you can unmute yourself to ask Dr. Peng directly. So I want to take the advantage to ask my question first.
Yeah.
So I noticed that when you do the simulation, actually you have homogeneous particle size in the turbulent flow. So for the LBM, you mentioned that the mesh size have to be kind of for a uniform mesh. Does this mean you have to use the smallest the mesh size to capture the smaller particle, even you have many big particles in your simulation?
Well, so when we say finite-size particle, basically, if we're doing DNS, the mesh size has to be smaller than the cosmograph length of the turbulent flow, right? So when we talk about finite-size particle, which basically means the particle size is larger than the particle diameter is like on the order of maybe at least a few times, or like 10 times the cosmograph length. So in this case, the particle, the diameter of the particle is usually covering like about like a 10 or 20 lattice or a grid mesh. So that's so when you have you have different size of particle in this flow, right?
Yeah.
When you have a different size of particle in this flow, of course, yes, you have to ensure that at least you have a sufficient grid mesh for the diameter for the particle, even for the smallest one. Otherwise, there is no way you can simulate the particle motion accurately.
Yeah. I suppose this could be very expensive. So when you introduce the particle latent flow, you introduce that there's some other cheaper way you can use the concentration to represent the particle concentration. But the problem is you do not have accurate model to consider what's the constitutive equation for the different concentration. I'm wondering, because you can run very expensive simulation, you can start a different concentration of the particle distribution. You can get the DNS data. I'm not sure if we can connect this two-level model. For example, I can use the very fine scale simulation as the DNS data to provide some knowledge to build the constitutive model for the low resolution model, and I'm considering how we can improve the efficiency and also the accuracy for the particle latent turbulent flow.
Yes. So what you just asked is what we like. Not just us. Is the whole community is trying to do is like how to how to like bridge these two. Like say how can we use the results of say fully resolved simulation results to help us better like say better create a better model for this lower level methods. But this is still very difficult. I'll show you an example. The only paper I as far as I can recall, there is only one paper actually successfully did this. So why is that? It's because say if you want to like say do the Lagrangian point particle, Lagrangian point particle basically assume that the particle is a point, is a mass point. It has no volume. Okay. So the physical condition for you to make this as a reasonable assumption is that the particle size has to be much smaller than the chromograph length.
Yeah.
Okay. So say the particle size has to be like 0.1, 10% of the chromograph length. Okay. So in this case, you can use point particle simulation. So the problem of directly using this guy, the fully resolved results to like direct the Lagrangian particle simulation means like you have to also do you have to do a fully resolved simulation for particle which is like 10% of the chromograph length.
Yeah.
What I'm make a direct comparison, right?
Yeah, the only thing you're missing for the point particle is you cannot get the feedback stress from the particle, right? So this means we need some model. We need some model build based on the fully resolved DNS simulation. This will give you some information how you can find back the subgrid. Because you use point particle, you do not have the subgrid interaction for the two-way coupling. But if you have fully resolved data, fully resolved DNS data can give you some information. Maybe you can build up some feedback stress generated by the finite-size particle. Even you use a point particle in the simulation, but if you can find correctly the feedback stress, I think maybe it's doable. This means you generate some you do not have subgrid. You do not resolve the subgrid information, but you build a model to represent the subgrid feedback. And this model is built up based on your DNS simulation, right? It's not arbitrary, it's not empirical, built based on the DNS simulation. I think
so right now, actually, in the Lagrangian point particle simulations, you can still have some feedback force, and the current way to do that is that you just you sum up all the the force of the fluid acting on the particle. Then you sum them up, and then you take the opposite.
It's kind of that way kind of empirical. I mean, you do not do this kind of by empirical way. You are doing this based on the data you generate. How to correctly generate the force is based on the DNS simulation data. It's not.
Yeah. That's actually a very good suggestion. I'm not sure, like this one may be something doing in that line. Is that in this case is that I use the fully resolved DNS to get how the drag force changes when you have a turbulent environment, and I'm not sure. I haven't thought about that. Like, how can I, if this is a universally good model, then how can I use this to guide to develop a better, like, say, point particle simulation method?
Yeah. I think we are using very expensive simulation to get we cannot just end at this point. We should think about how we can use this knowledge, right?
Yeah. That's true. Yeah.
Great. Thank you, Chen.
Okay.
Any other question from our audience? Kaishan, do you have any question?
Really good report. So I just want to could you please introduce the interaction of the particle and the fluid flow?
The introduction.
Yeah, interaction.
The interaction between the
I mean, so what kind of particles and flows in the real world?
Okay. Yeah. So of course, that's depend on the applications, right? So in many fluid particle system can be described in this as this particle flow system. For example, you have the, like, dust. If it's dust, then which meaning very fine particle, and I think the like tracer particles in the PIV experiments can also be classified as this dusty particle. And in this case, particle will not have the feedback force of the particle on the fluid phase can be totally ignored, and it has to be ignored. Otherwise, the PIV test will not be accurate, right? And if you think about a slightly denser particle, but the particle is still very small. For example, in the fluidized bed, like in the fluidized bed, the core particles has the diameter of a micron, then this is more like in this range is the equivalent Eulerian or Eulerian range, meaning the particle velocity is still can be written as the expansion of the fluid velocity. Then I think then I'm not sure about this really depends on the physical problem. Lagrangian particle, point particle, I think like people doing like sandstone, they are more like they are more using, I think they're most of them use this Lagrangian point particle, a sandstone, like a sand particle in the high ensemble stone. And fully resolved, well, those are large particles. So it depends, right? I mean, it depends because it's a ratio between the particle diameter and the common growth length. So it's
So your simulation is focused on pretty large Stokes number, right? So the particle initial will be very important in your simulation when you.
Yes. So I don't think I think like once you talk about fully resolved, once you talk about large particle, then I'm not sure the current definition of the Stokes number is still useful.
Okay, but the particle initial were dominate the flow. The particle were not exactly follow the streamline. Right?
Yeah. So it depends. Yes.
Okay, so I have another small question. So is that possible to simulate some particle, like active particle, such as such as you know, some fluid with bacteria?
You mean the particle can deform, right?
You mean deformable?
Or have live active particle?
Active particle. Okay. This may be quite different.
You mean like a red blood cells, or like
no,
a
the
bacteria?
active particle means that there is some active force can generate on a particle.
Okay, yeah, that's I don't do this type of research, but I know many people working on that. Of course, I'm not sure if you know the Professor Huang Haibo from I think he does a lot of like the fiber or something, or I'm not sure what we call that. So and for that, I think it's maybe it's maybe more suitable to do it with the inverse boundary method.
All right. Okay. Thanks. Thank you very much. Very good report.
But LBM certainly can do that, I think.
Okay. Thank you. Thank you very much. I have no other questions.
Yeah, you're welcome.
Yeah, by the way, Kai-Xuan Zhang is a previous postdoc at the Tsinghua University, and now he is a faculty member at the Tianjin University.
Nankai. Yeah.
Oh, Nankai University.
Yeah.
Okay.
Thanks.
Okay, so then if we do not have any other question, then we'll end here today. Thank you very much, Dr. Pen, for the very interesting talk. Then
thank you.
This is the ending talk of our 2022. And so we will see you again in next year.
Yeah.
See ya.
Yeah.
Thanks.